Are we ready to go?
Yep.
Yeah, good evening. Thank you very much. I'm Michael Walker with the Data Science Association. Thank you for coming this evening. We have a really special presentation tonight for you. To my left is Jordan Boyd Graber. He's an assistant professor at the University of Colorado Boulder. He specializes in machine learning, and he has a wonderful topic in terms of machine learning and human partnerships. And we were just talking, for the last few years we have made incredible strides in machine learning, but more on the theoretical basis. We really haven't done a whole lot in terms of applying it to real-world situations. And while it's very important that you have a deep theoretical knowledge to avoid a lot of the problems that you'll run into when you start to apply it, it's really time for us to start applying machine learning to real-world situations. And for those of you who have done that, like myself, it's very, very difficult. It's very difficult because you need a partnership with the intelligent machine and the human. And to get that right is tricky. And I think that that's the future of data science. That's where we're going. It's not so much machines or robots that are going to replace all the human jobs. There's a little bit of that in terms of automation. But the real goal is to have humans partner with intelligent machines. And machine learning will be an important tool in terms of doing that. Just a quick announcement, we're going to, our next meetup will be August 9th, I believe, in Fort Collins. It'll be the Rocky Mountain High Performance Computing Symposium. We'll post that up there. And then I think we'll be back in Denver in September. We have a couple of speakers on Spark. I don't know if you guys know much about the Spark ecosystem, but it's really starting to mature and really looking good. And we'll have some speakers on that. And then in October, I think we're going to be back up in Boulder. And we'll have Richard Loft and another speaker on the future of high-performance computing. So thank you again for coming, and thank you, Jordan, for presenting today.
Okay, great. Thank you very much. Before I get started, let me first say that I welcome interruptions during the talk. I'd rather this be interactive, and so I'm going to dim the lights a little bit for the sake of the video capture, but please stay awake and ask questions. Okay, so let me get started. Machine learning is an ever-increasing part of our lives. It tells us what to watch next in our binge watching. It's putting skilled people out of jobs and also trivia contestants. It's telling us what emails we should read. It's telling us what we should buy next, and gatekeeper for all the information that we ingest by way of, say, rankings on search engines. But despite its ubiquity, it still remains for most people a pretty opaque black box. Who knows what it's doing? It seems to be doing it well, but you don't know why it's doing stuff. You don't know what's going on inside that box, and if you have a problem with it, tough luck. And there are obviously exceptions to that, but this is the general rule, and hopefully that isn't too contentious a point. Most of the machine learning that we see is pretty much a black box. And I think that's a problem. And I'm going to talk about some of my research and what I've done with students to try to open up this black box a little bit, to create algorithms that can inform people in an interactive way, to collaborate with people to solve interesting problems, and for other things, to also compete with humans in interesting games. And I'll tell you why I think that's important a little bit later. And in the end, hopefully to create algorithms that understand us, to have empathy, and to have a real connection with people. Okay, so with that introduction out of the way, let me first talk about informing humans in an interactive way. So, big data is a challenge. Every second, 500 new blog posts appear, 34,000 tweets are tweeted, 30 gigabytes of data are uploaded to Facebook, and much of this is unstructured text. There's no XML or semantic web data to tell you what it means. It's just text, and good luck if you want to try to figure out what's going on in there. And this is a big problem for a lot of communities. So people at three-letter agencies want to figure out if something big is happening in the world that they don't know about. Companies want to know if you're saying something bad about your Chipotle burrito, and if they need to do something about it. Journalists want to know what's going on in the world, and is there a new revolution that's fomenting somewhere? Can we get people there to report on it? And humanists are increasingly not doing close reading, but they're doing what's called distant reading. They're trying to understand the entire work of Lope de Vega or Elizabethan playwrights, and they don't have time to read everything word by word by word. They're using machine learning techniques to try to read, in quotes, much more than they could possibly do in their own lifetime. And a common solution is something called topic models. So show of hands, who has heard of topic models before? Okay, all right, so quarters, so it's good that I have a little bit of an explanation coming up. Okay, so what is a topic model? At sort of a 1,000-foot view, a topic model takes as input a bunch of documents, where documents are just a bag of words, and then the output is some number of k topics, where k is a number that you specify beforehand. And so if, for instance, you put in as input, say, a decade's worth of the New York Times, and you ask it for 50 topics, here are 3 of the topics that you get. And each of those topics is just a collection of words, actually a probability distribution, but we don't need to get into that right now. And so you get one topic that's sort of a technology topic, you get one topic that's sort of a business topic, and you get one topic that's sort of an arts topic. And you can look at all the topics, and you can get a sense of what's going on in this data set. So in the New York Times in the early 90s, they talked about technology, they talked about business, and they talked about the arts. And if you're interested in one of these topics, you can zoom in and find out more what's going on. So we worked with some folks while I was still at Princeton to try to understand what makes a good topic model. And I'll talk about that in a second. But before I do, any questions about sort of the big picture of a topic model and what's going on? Yep.
So what actually evaluated as a good topic?
So you have the words in the document, and a topic model is trying to find out the best low-dimensional representation of how to reconstruct those documents. And so these are probability distributions that when you put them together does a good job of explaining, on average, the documents that you see in the collection. Yeah. Yep.
Are you going to cover how best to select the number of topics?
Yeah, a little bit. That's sort of what I'm getting into next. I won't get into the nitty-gritty of that, but I'll give an intuition, yes. Okay, so how do you know what's a good model? And so a good model could be either the algorithm that you're using or, say, the number of topics that you select. And so if you ask a statistician, how do we evaluate a statistical model, they'll say use held-out likelihood. And so that's the traditional way of evaluating these sorts of models. You have some held-out test data set, you have some model, and these are probabilistic models, so you can ask what's the probability of these things, and whatever number is highest, you take, you say that's the winner, that's the number of topics I should use, that's the parameter settings I should use, or whatever else. So, if this is true, is that what people actually care about? And I would argue that the answer is no. If you look at any paper or any Meetup talk where people introduce topic models, you're going to see a figure that looks like this, showing, for example, topics from science over decades, or from nature. These are things that are being talked about, and so they actually show what the topics are. And this is true even if you're not looking at English. This is all of the languages in Wikipedia, one topic. It's also true if you're not looking at a natural language at all. You can do topic modeling, say, on source code and discover, for example, network security type stuff and logging type stuff as topics that get discussed in your source code. And so people seem to care about what these topics are, and do they make sense, and do they tell an interesting story? So how can we measure this? And so statisticians like measuring things, and so that's why we have held out likelihood as a way of evaluating models. But if you're actually showing the results of this analysis to a human, does that match with what the human cares about? And people put so much faith in these topic models that they even use the topics to draw conclusions. So this is a really interesting paper from about a decade ago where someone used topic models to tell a story about how statistics had taken over computational linguistics and linguistics overall. And I find this sort of ironic because they are linguists who have adopted a statistical approach but don't bother analyzing the approach that they take in sort of a way that a linguist would do by actually asking people, is this acceptable or not? Which is an evaluation that linguists help develop. So what we're doing is we're going to try to evaluate whether these topics make sense. So let's say that this is a topic. So this is not a real topic, but sort of one to explain what we're going to do. And what we're going to do is we're going to take some other word from some other topic and stick it in there. And let's call this the intruder word. And so if you watch Sesame Street, this is like one of these things isn't like the other, one of these things just doesn't belong. And the hypothesis is that if we can ask someone to find the word that doesn't belong, and they can, then the original topic made sense. Okay, so any questions on this task and why we can use this to evaluate how good a topic is? And we did all of the things that you should do. We randomly selected the topic, we randomly selected the intruder word, varied all of those, and did multiple replications with people. And so now we can compare the traditional evaluation, this held out likelihood evaluation from statistics, with our metric, which we call interpretability. And so the interesting thing is that there is a negative slope as you increase and improve the traditional evaluation. The interpretability goes down. As your models get fancier and more complicated, it gets harder and harder for a human to understand them. And the slope is slight, but statistically significant. And so the moral of the story is that if you're chasing after held out likelihood, you're going to make your models confusing and worse. And since we've done this, people have improved our method. They've automated it, so you don't actually need a human in the loop to evaluate it. They've applied it to more structured topics and topic models that discover phrases, not just single words. And people have built models that try to optimize this directly. And so I'll stop here for questions, but next I want to talk about how we can use the insights that I got out of the first part of my talk to create models that try to reflect what a user wants to see in their output. And so what topic models were before is sort of a take it or leave it proposition. You do your analysis, you get some topics out, and if you don't like it, tough. And so now we're trying to develop ways to make topic models that can actually respond to what a human wants. Okay, yep.
Can you go back 2 slides?
Mm-hmm.
What are the acronyms there?
Yes, right. So these are various flavors of topic models. And so this is the correlated topic model, latent Dirichlet allocation, and latent semantic indexing. And so latent semantic indexing is if you use linear algebra to find out what the topics are. Latent Dirichlet allocation is if you assume that the distributions come from what's called a Dirichlet distribution, which has some nice linguistic properties. And correlated topic models are if you assume that the topic distributions come from a logistic normal distribution. So much, much more difficult to implement and much, much more complicated. It gets higher held out likelihood results, but lower interpretability scores. So it's part of the same story. The more complicated you get, the worse you do in terms of human interpretability. Yep.
I know it's probably difficult, but it's possible there is some kind of optimum value.
Oh, yes. And I don't want to overstate my claim too much. And so this is exploring a very narrow range of the parameter space. And so if you zoom out, these things are going to be quite well correlated. Both of these can pick out really horrible models and tell you that you have a really horrible model. But we chose the parameters that we looked at as sort of typical values that people use in practice. And so in this narrow region, there is a negative correlation. So you're absolutely right, and I don't want to overstate my conclusion too much. So thanks for keeping me honest. Okay, great questions. Okay, so now we know what makes a good topic model and a bad topic model. How can we do something about it once we have a bad topic model? So we've done some work with the National Institutes of Health, the primary funding agency for medical and biological research in the United States. And they want to try to understand what they're spending billions of tax dollars on in terms of funding. So they asked us to take all of the funded proposals and run a topic model on it. So we did that. We did a 700 topic model, and this is topic 138, and they didn't like it. So why didn't they like it? It had a couple of words related to the urinary system mixed in with words from the central nervous system. And this is complete anathema to folks at the National Institutes of Health. These are covered by different institutes. They should not be together in the same topic. And so they said, if your model does this, then we can't use it. Forget about the 699 topics that didn't have problems, but this topic, no go. We should throw the model out. And so with my student Yining, we worked on trying to correct problems like this. And so one way you can think about this is that all of these topics are distributions over words, and a priori, they're uncorrelated distributions. Any words can appear together in a topic. You can have computers appear with monitors. That makes sense. You can also have computers appear with tacos, and that makes less sense. But to the model's perspective, all of that is equally likely and possible. And so what we can do is we can add in some constraints. And so if a human tells us that president and constitution should be positively correlated, we can add that in as a constraint. Or if spinal cord and bladder shouldn't appear together in a topic, we can add that in as a negative correlation. And we can encode these probabilistically into our model. And so let's see what this looks like. So here's the New York Times data set that I showed at the very, very beginning. And here are 20 topics. And if you look at topic 1 and topic 20, topic 1 is about the Russian Federation, and topic 20 is about the Soviet Union. And this is New York Times documents from about 1985 to 1995, so it makes sense you'd have both. But someone might look at this and say, well, they're really part of the same historical narrative, so they should be together in a topic. So you can add in a constraint that says something like Boris Yeltsin and Mikhail Gorbachev should be positively correlated. And when you do that, topic 20 now becomes about the Soviet Union and the Russian Federation. Topic number 1 becomes about democratic movements in other countries, particularly South Africa. And the other topics that you were ostensibly happy with don't change too much. They change a little, but not too much. And so this is what we're trying to do, that we have an analysis. The computer might have made some mistakes. Maybe it lacks some world knowledge that the human has, and we can encode that human knowledge as constraints and improve the models so that if you have a pesky boss who wants everything to be just perfect, you can fix the problems that he sees. Yep?
When you're getting those problems, can you trace the problems down and say, okay, how did the computer come to correlate taco with computer?
Right, and so that is a really good point. We don't have a good automated way of doing it, but like for the spinal cord and bladder issue, our first argument was, well, that's not really a problem, and so we dug into it, and there was a little line of work where people with spinal cord injuries often have rehabilitation problems with bladder control. And there's a line of work discussing that, and the computer put them into the same topic. And that's basically what happened. It's a small fraction of articles. It's not really representative of either of those two fields, but it sort of latched onto that and carried it through, and that's what happened. So often there is a story you can tell about why this happens, and but we don't have a good automated way of doing it, or we especially don't have a good way of telling the computer to avoid those kinds of things. Yep.
So it's similar to label data and neural networks, and use backprop to kind of minimize that error. So you're labeling, you're kind of assisting the statistics here. How does a statistical method minimize the error with your guidance you give it?
Yeah, so there's, if we want to put everything in terms of neural networks, you can think about this as an unsupervised model, and it's just trying to minimize reconstruction error, where the reconstruction error is measured in terms of tail divergence. And so since everything is neural nets, and if that's what you came for, you'll get that later on in the talk, that's the way to think about it in terms of neural networks. We don't have a direct supervision signal. I'll talk about a variant of topic models with a supervision signal at the very end of the talk, if I get there. And we'll see how that works in that case. Good question. Okay, so, all right, so let's go back to topic 318. And it mixes these things up, so we can add in a constraint that these two things should be separated. And so if we do that, if we add in that constraint, we separate these things out, and we end up with just one word, urothelial, left in here, and we talk to the folks at NIH, and they say that that's actually connected to the central nervous system stuff, so that's okay. We can live with that, and so success. And so what we're doing now is we're working with real agencies who have problems like this. And so the FCC gets a lot of complaints about Comcast and Time Warner and everything like that, and they have very highly paid lawyers basically sorting these complaints into buckets. And that's a huge waste of taxpayer money. And so we're working with them to try to figure out ways of using topic models to speed up that process. The General Services Administration has a lot of data of federal employees complaining about their jobs. And again, they have very highly paid government workers sorting things into buckets in very deliberate, methodologically sound ways because they can't appear partisan. And again, it's a waste of money. If we could have an impartial machine do it, we could save a lot of money and time. And similarly, other funding agencies like the NIH wants to understand what they're funding and to make a case to Congress that they're funding useful things. And so we're working with these folks to try to speed up their process of analyzing their data. Okay, so next I want to talk about another kind of collaboration. And before I get into that, let's take a step back and have a little history lesson. So at the end of World War II, there was something called the Nuremberg trials. And so a big problem was that we wanted justice to be delivered to the people of Europe. And we had 4 judges from countries that spoke 3 different languages, and there were a total of 14 languages spoken by all the defendants and all the witnesses, and not everybody spoke a common language. And so the traditional way of doing interpretation at that time was that person A would speak a sentence, they would finish the sentence and pause. Then a translator would come and repeat the sentence. And so you basically say everything twice. And there was a back of the envelope calculation done, and it would take about a decade to get through the Nuremberg trials if we did translation in that way. So one of the reasons that it's hard to do interpretation is that there are some languages that have very different word order from each other. So, for example, German and Germanic languages in general, like Yiddish, after which Yoda's sentence patterns are based on, because Frank Oz had some exposure to Yiddish, put the verbs at the end of clauses. So when you at the dark side look, careful you must be. And so this is why interpretation is hard if you don't wait for the end of a sentence. And so this is true in German. So if you have this nice German sentence, ich bin mit dem Zug nach Ulm gefahren, the verb here is at the end of the sentence, and if you wanted to translate that into English, in sort of a traditional English word order, you could translate ich to I, and then you have to wait until the end of the sentence, and so that doesn't really buy you anything. So what do real interpreters do? So they have a number of tricks, and what we'd like to do is to be able to figure out what they use in order to solve these sorts of problems. Can we teach machines to use them? And can we teach machines when to use them? So two different questions there. So can we teach machines to use these tricks, and can we teach machines when to use them correctly? And then can we actually have a collaborative relationship with interpreters? So right now, interpreters are the status quo of how translation is done. They don't wait till the end of the sentence. They stay just a couple of words behind the person they're translating. They're very highly paid, very expensive. They take years to train, and they're very hard to get. But they're the gold standard, and it would be nice if we could lower the cost of that so that more people could have access to high-quality interpretation. Okay, any questions on the setup of this new collaboration between machines and humans? Yep.
Like, doesn't Google already have an app that does this?
Right. So Google translates entire sentences. So it will translate an entire sentence, and one trick that they do is if you type in a partial sentence, they will translate it. But you will notice that those translations can change dramatically as you type in one additional word. And so interpreters can't do this. Once you say something, you've committed to it, and you're done. And so unlike Google, interpreters don't have the option of saying, oops, I didn't mean that he wanted to eat your children. I actually meant he wanted to feed your children. And so Google doesn't have that. Google has that option. Interpreters don't. Yep.
So I think the Google app guesses what the meaning is, and usually it's a pretty good guess, but it's not always accurate. It seems to me that you have different accuracy demands. So, for example, in a legal proceeding, you have to have a very accurate translation of what that person said, or it could change the entire proceeding. Or in healthcare,
right.
If you're interpreting a diagnosis from patient to doctor, if you get that interpretation wrong, it could cost somebody their life. Right. Yeah, and so here we want to have an algorithm that commits when it knows the answer, and it doesn't have this option of saying, oops, I didn't actually mean that. Good clarification. Okay, so with my student Alvin, we created a process for trying to do this. And so we basically use the same technology that Google uses for auto-completion to replicate one of the tricks that human interpreters use. And so if you type a Google search into Google, it tries to predict what the next word is going to be. And so we want to do something similar. We'll try to predict what the verb is going to be. And if you can predict the verb, then that unlocks a large part of the sentence. And so I want to be very upfront about this. We're going to be very bad at predicting the verb. But if we can do it well enough, and we end up being able to do it about 14% of the time, you can speed up your interpretation so that you can get ahead of where the speaker is and make good predictions about what the verb is going to be in languages like German and Japanese, where the verb comes at the end of the sentence.
And so the way that we do that is that we take a bunch of German sentences, we find the verb, and then for each verb we build what's called a language model for that verb. And so each of these you can think about as a little machine that predicts what the verb is, what the words are given the verb. And then we'll use Bayes' rules to turn this around so that we can, given a bunch of words that we've seen in German, it will try to predict what the German verb is going to be. Okay, any questions on that? So think of these like a couple hundred autocomplete machines that can give us a verb given some German words. Okay, so we use Bayes' rule to figure out what the verb is going to be, and most of these predictions are totally wrong, and if we use them without verifying, they lead to horrible translations. So we need to figure out when to trust these predictions. And so we use something called BLUE, which is basically a way of evaluating machine translation quality. It correlates well with human interpreters. So going back to the first part of the talk, we want to have a measurement that corresponds to what humans think is a good translation. But unlike the traditional BLUE, if you're familiar with it, we're going to have many different translations over the course of the sentence. So over time, as we translate more and more of the sentence, as we get more and more of the sentence, we're going to have many different translations. And how do we sort of get a total score for how well we did over the entire course of the sentence? So what we're going to do is we're going to take a discrete integral of all of these different scores and then call that our overall total. Okay, so this probably isn't very clear yet, so let's give some examples of different ways you could translate a sentence. And we're going to call these policies, so different policies about when to trust a prediction. So first up, let's look at a psychic policy. So this is impossible to implement in practice, but it's sort of a good thought experiment. So let's say that you have a policy that when you see the first word of German of a sentence, you can translate the entire sentence perfectly. And so you get input and you say, he went to the store. And that's right. And so you get perfect. You get a perfect score because you were able to capture all of the translation very early on. Okay, so that's impossible, but it's a good reference point. Now let's look at monotone translation. So this is what you probably imagined translation was when you were a kid. This is basically words come in one at a time, and you basically look them up in a dictionary and you write that down. So if you get ist zum Laden gegangen, you basically get he to the store went, not a very complicated sentence, and so you can do an okay job. You don't get a perfect score, but you do okay. And the way that Google would do this, or any existing batch translation system, is it would not translate anything until it gets the whole sentence, and then you get a perfect score at the very end. But you lose out on a lot because you weren't willing to take any risks, and so you lose out on all of the stuff that came before. What we want to do is to get the best of both worlds of these two, where we want to be able to translate simple words that we're fairly certain of early on. We want to be able to predict the verb when we can, and then translate whatever else we can as soon as possible. And so here we're hoping to get the best of both worlds. We don't make the dumb mistakes that the monotone policy that prevents us from ever reaching the very top. And we want to be able to take advantage of predictions and also whatever greedy translations we can do. Okay, any questions? All right, so this is our setup. And so we use something called imitation learning so that we can teach the machine when to trust these predictions. Imitation learning has been used a lot in robotics for teaching machines how to fly a helicopter or fold towels or drive. But it hasn't really been used that much for language, and that's what we're doing here. And so sort of a cartoon version of this is that we're going to create an oracle that is the best that you can do given a fixed translation system. We're just trying to learn when to predict the verb and when to trust the prediction and the translation. So consider the translation algorithm fixed. And so there are a number of actions that you can do, and in this case, this is the optimal path. You first wait, then you predict the verb, then you wait some more, and then you commit at the end to finish the sentence. And so this is what you should do. And so we train a classifier to try to mimic this using cost-sensitive classification, and then we get a classifier out of this that cannot match the optimal. It's like learning how to drive your very first time out of the driveway, and your teacher is a Formula One driver, and so he's taking turns at 200 miles an hour. You can't do that, and so you basically wind up in a ditch immediately if you try to emulate him. So what can we do? If our teacher is too smart, let's make a dumber teacher. And so what we do is we have the dumb student that came out of a too smart teacher, and so we'll combine the two together. So this is no good, and so we'll basically just flip a coin. And at every time step, we're going to flip a coin and either select what the too good expert did, or take what our too stupid student did. And then we get a corrupted teacher out of that, and that becomes our new teacher. And so we build a new classifier out of that, and we get a new set of actions out of that, and we keep doing that until we converge, that the teacher and the student are at the same level, and then we get a new policy out of that, and this is what we actually learn. And this algorithm is called Searching to Learn by Haldane and Marku. Okay, so let's compare how we did. So at the end of the sentence, the optimal is obviously doing better than everything else by definition. Our learn policy is doing better than batch translation and doing better than monotone translation. And so this is at the end of the sentence. And so let's take a look at what's happening over the course of the sentence. So batch, at the very end, does well, but up until the end, it's doing nothing. So if you remember, batch waits until it's seen everything to make a translation. Monotone does okay throughout, but then falters at the end. This is because German word order is a lot like English word order, except for verb final sentences that have the verb at the end, and so it screws up at the end. The optimal policy does better than monotone by definition, and then we have a learn policy that lags behind monotone because it's sacrificing some speed for a better overall performance at the end. And so this is for German. I won't show you results for Japanese. It does a little bit better on Japanese in terms of learning the policy, but much worse on predicting verbs, so it isn't a very good story. But for Japanese, monotone does less well because you have freer word order. Yep?
I'm just curious, in batch, in translation, we found that very simple algorithms with lots of data work best.
Yes, exactly.
How does that differ, if it does differ at all, from monotone optimal?
Right, so I think it's basically a truism that more data always helps. And so here we're sort of looking at two orthogonal things. So if we hold translation fixed and we try to learn a policy, more data helps the policy, and more data would also help the underlying translation algorithm. So you can improve either with more data. Yep.
How do human translators do on this same?
Yeah, so I don't have slides for that. We have a paper that we're going to present in Berlin later this summer. They do better than this, obviously, but it's very hard to get sort of pro translators. If you sort of pull someone off the street and ask them to interpret, they basically curl into a ball and cry. So it's a really hard task. It's something that requires years of training to do. So the very top translators predict about Well, so I can't say that they predict. They lag about 4 to 5 words behind the speaker, and they have different tricks for doing that, and so they're very, very good. They are much, much better than any algorithms that we have thus far. And so I'll talk about some of their other tricks in a second. Yep.
How do you get over 1.0 on the smooth average?
This is in terms of a BLUE score, and so BLUE scores are unbounded, and so it's hard to interpret what a BLUE score actually means numerically, but higher is better, and it can't go below 0. So yeah, so the top of the y-axis doesn't really mean anything. Yep.
How did you get optimal?
Right, so yeah, I totally didn't mention that. You can basically do a dynamic programming algorithm to figure out the optimal set of policies. And so long as you assume that you cannot do any oops, I didn't mean that sort of corrections, it's something you would work out in your sophomore algorithms class. You basically have a big matrix, and for each cell you consider all of the ways you could have gotten to that cell using some combination of actions like predicting the verb, predicting the next word, predicting, accepting the output of the translation algorithm, and all that.
So it goes through every option post, and then it finds the optimal.
Exactly, yeah.
Are there significant time differences?
Right, so we did not compare that, so to sort of make the time comparison fair, we sort of pretended like we had a clock that ticked every word, and so we did that comparison. But yes, absolutely. So batch only does one translation, and so that's going to be the fastest. Monotone is going to be next fastest because it's doing it's still doing a linear number of translations, but they're fairly stupid ones. And then ours is going to be quite a bit slower because it's doing many more translations, it's doing prediction on top of that, and so it's going to be much slower. But I think that you can do it at the same time scale as humans do it, if not at the same quality. Yep.
How complicated are the sentences you're feeding into it?
Yeah, so these are sentences from German radio reports, and so not horribly complicated. It's not like legal documents or things like that. But they're not child sentences either. So yeah, so lots of weather reports, lots of sports reports, and things like that. So a good range of stuff. So here's an example of a sentence. And so here you get Bundesumweltministerin, and then it knows at the time who that person is, so it's able to predict that even before it hears that the next word is going to be Merkel, so this was before she was Kanzlerin. And so it is able to predict this and give this nice translation. Just with the input Bundesumweltministerin, it's able to translate that to Federal Minister of the Environment, Angela Merkel. And then it predicts, after it's seen this, so Federal Minister of the Environment, Angela Merkel, the draft, then it predicts that the verb is going to be shown. And that's not quite right. And so it loses out because the actual verb is vorgestellt, which is basically presented. And so one could argue that these words are similar enough that you really shouldn't count this as an error, but the way that we set things up, it loses out on getting any credit for making this prediction. One could argue that this is close enough. There are ways that we might get around this, but we haven't done that yet. Okay, and so thus far I've only talked about verb prediction, so that's something that we knew relatively early on that human translators did, and there are other stuff that they do as well that folks have examined in the psycholinguistics literature. And what we wanted to do is to try to make it possible for machine translation algorithms to use more of these tricks. And we were able to do this by rewriting some of the training data so that it looks more like the tricks that human interpreters use. And the only thing I want to say about this is that this improves batch translation as well. So we didn't expect that this would happen, but one very common problem when you do machine translation from German or Japanese into English is that it doesn't know what to do with the verb. And so it just gives up and drops the verb. And that leads to a bad translation. People can figure it out, but we like to have verbs in our sentences. We verbs in our sentences. And so what we can do is, if we use the same tricks that interpreters use to train our algorithms, the verbs don't disappear. And so if we pacifize the verbs or break clauses into smaller segments or use simpler verbs, we can have better tools to teach machines how to translate sentences. So this was a nice side effect of some of the stuff that we were doing. But I want to be clear that I'm not arguing that we should get rid of human interpreters and replace them with machines. That is not the world I want to live in, trusting high-level negotiations between nuclear-armed countries to a machine. Instead, I think we should learn the lesson of chess. And so chess is an interesting game where the best player, loosely defined in the world, is not a human, it's not a machine, it's a human and machine working together. And the best chess teams in the world are a human and a computer working together. And I think this is what we should have for high-level negotiations. Humans have a lot of intuition. They know what's polite to say and what's not polite to say. They know when they should be super cautious and not commit early, even if it results in a delay. But machines have a lot of advantages. So humans can remember about 7 plus or minus 2 things at once. Machines have a much wider memory. And so machines are able to cache a lot of translations ahead of time and pull them out as needed. Machines are able to take notes perfectly and have perfect memory. If we had a human and machine working together, we can get the best of both worlds. And sometimes humans can't afford an interpreter. So if you just have a machine, it's not going to be as good as a human, as a master interpreter, but it may be better than the alternative of having nothing. Okay, next I want to talk about the inverse of cooperation, competition. So how can we make machine learning algorithms that can compete with people? So before I jump into that, any questions?
So just I wanted to add that
Yeah.
as we humans use in our linguistic tasks, we have something called context.
Exactly.
How to, it seems like it's an ingredient, one of the most important ingredients on this.
Yeah, exactly. And so, for instance, one thing that we notice is that humans tend to repeat themselves, and they'll often use the same verb in 3 sentences. And so, I demand that you give me free pizza. I demand that you provide me a ride to the airport. I demand yada, yada, yada. Our algorithms that try to predict the verb don't pick up on clues like that. And they sort of start each sentence off with a clean slate and don't use context. Yep?
I don't know if you're just going to come up after the algorithms that compete with humans, but they're going to have a translation aspect?
Yeah, so we're done with translation now.
Okay. Have you tested a lot of the computers translating versus the humans and maybe translate back and forth? Conversation?
Yeah, so not as much as we would like. So we've done experiments comparing how well either humans or machines can predict verbs, and so just looking at a very limited part of this. That's definitely something that we want to do next, and we're thinking about writing a grant to do that. So if you have good ideas for fun ways to do that, let me know. one thing that we're thinking about is how we could have a Centaur-like setup as with chess, where you have a human with sort of a heads-up display, and what information can you give to the human that would allow them to translate most effectively without distracting them. Okay, so now I want to talk about humans competing with computers in a setting called Quiz Bowl. And believe it or not, this is not too different from the interpretation stuff that I talked about before, but give me a minute before we get there. So who here has heard of Quiz Bowl before? Okay, yeah, not too many people. Colorado has not had a lot of Quiz Bowl presence in the last 3 decades, unfortunately. So rather than trying to explain it, I'm going to read you a Quiz Bowl question. And the way this works is that you have 2 teams, and you get to interrupt the moderator, the person who's reading the question, when you know the answer. And the questions are structured in such a way that the earlier you answer, the smarter you are, because the questions are structured so that you have very obscure stuff at the beginning and then more obvious stuff at the end. Okay, so shout out the answer when you know it. With Leo Szilard, he invented a doubly eponymous refrigerator with no moving parts. He did not take interaction with neighbors into account when formulating his theory of
Relativity.
Close, but not quite, of heat capacity. So Debye adjusted the theory for low temperatures. His summation convention automatically sums repeated indices and tensor products. His name is attached to the A and B coefficients for spontaneous and stimulated emission, the subject of one of his multiple groundbreaking 1905 papers. He further developed the model. Yeah, Einstein, yes. And so.
No, Bose.
That was that is not so. Bose did not collaborate with Szilard on a doubly eponymous refrigerator.
It says Bose. Bose described Arnold's.
Yes, exactly.
I thought we were predicting what was continuing on the sentence.
No. So this is all about Einstein. All of this is about Einstein. And so so Einstein did all of this, and so most people don't know about his work with refrigerators. But if you do know about that, good for you. You can answer the question earlier and beat your opponents at Quiz Bowl. So how is this like interpretation? You have a stream of words coming in, 1 word at a time, and you need to figure out what to do with them, and you need to make a prediction, but you don't want to do it too early or you'll be penalized. And so this is like predicting the verb in interpretation. So you have a bunch of words coming in. If you predict the verb wrong, and you say, I want to eat your children, that's bad. But if you can predict, I want to feed your children very early on, that's good, and you get a reward. So a lot of the same machine learning tools that we used in the previous section we'll be able to use here, but with a different goal, trying to compete with humans rather than collaborate on translation. Okay. Does the task make sense to everybody? Okay, all right, so one thing I usually need to point out is how this is different from Jeopardy. And so just like in the translation section, I need to talk about how it's different from, say, Google or Bing Translate, where they have an entire sentence and they translate an entire sentence. This is not Jeopardy, where on Jeopardy, you have the question displayed, and what you don't see at home is that when you're actually on stage, there are these yellow lights that count down next to the question. And even though the players have signaling devices, buzzers, as they're called, if you buzz in before that countdown reaches 0, you're eliminated from the question. So it's a lot like batch translation. In Jeopardy, you can only answer at the end of the question when Alex is done reading the question. You cannot interrupt Alex. That would be impolite and also bad television if you did that. So Watson was an incredible achievement, but it was playing a simpler game where it had a complete question and it needed to answer a complete question. Here, we're trying to decide when we know enough to interrupt a question to answer. Okay. All right. So there are 2 parts of this task, as I just alluded to. One is figuring out given some question text, what should I answer, and when to buzz in. So I'll talk about each of these in turn. So first, figuring out how to answer a question. So with my student Mohit, we developed a way of mapping text into some high-dimensional space. And you may be familiar with things like TF-IDF that maps into spaces. And so you can think about that intuitively. We're going to be doing something a little bit more complicated, but if that's a good intuition for you, keep that in mind. And so we have a bunch of space. We have a bunch of, say, Wikipedia pages with information. That gets mapped into some vector space. And when we have a question that comes in, that gets mapped to the same vector space. And hopefully similar questions will be close in the vector space, and things that are very different, like gummy bears and Pokemon, should be far away from Qatar and Bahrain. And so we have some question text. What we want to do is we want to put it in the same space as all of our possible answers, and whatever it's closest to, we'll answer. Okay, so at this point, we want to be able to do better than just simple TF-IDF type weighting schemes that ignore, say, the relationship between questions. So China and Taiwan are both possible answers we can give, but these are also words that can appear in other questions. We should use that information. And we want to be able to use learned features and dimensions, not the arbitrary words that we start with. And so to do that, what we're going to do is we're going to assume that every word lives in the same vector space. And when we have a question, we want to be able to map all of these disparate words that live in this vector space into a single vector. And so let's say this is our question. One thing you can do is you can just average the words. And if you've heard of things like word2vec, you can think about these as word2vec vectors. And so you can just average them, and that's sort of the straightforward thing that you can do. But what we'll do instead is that we'll map them through a nonlinearity into a new point in our vector space. And then, why stop there? We'll just keep doing that for another couple of layers, and we'll actually use 5 layers of nonlinearity. And the question that you should be asking now is, how do you figure out what these vector representations are? And so the way that we'll do this is we'll randomly choose some sentence and see where it lands. And so each sentence has an associated answer that we should be answering for this question. And what would be great is if this question lands next to the answer that it should be giving. But there could be other answers that are closer, and so we'd get it wrong if we were actually playing a game. So what we'll do is we'll update each of these word vectors to push it closer to the right answer and push the wrong answers away. Okay, and this is called warp. It's a nice technique from Jason Weston at Facebook. Okay, so that was a very high-level overview of how we answer questions. There's more details in our paper, but any questions thus far? Yep.
What sort of neural networks are you using?
Right, so we call this a deep averaging network, and so it's relatively simple. Just average, nonlinearity, nonlinearity.
You say you average those words, but like, what does that mean? Like, how do you average them?
Right, so each word is a vector. In this case, there are 4 words. So we add them up, divide by 4. So like high school averaging. And then that becomes a new vector that we put into a nonlinearity with some transformation, and then that gives us new output.
Like what's the space in which each word is a vector?
Yeah, so it's a 400-dimensional vector space. Okay, so we can project this 400-dimensional vector space into 2 dimensions, and we can see where things land. So, for example, here are all of the US presidents, and you can see sort of clockwise going through time We have the founding fathers, 19th century presidents, 20th century presidents, and we do get some weird stuff here. So we have Martin Van Buren hanging out with the 20th century presidents. I have a theory about why this happens. Anyone want to take a guess? You can see, we can compare theories. Yep.
He was like Andrew Jackson's campaign manager, so he was he was a politician.
So perhaps he presaged all the nasty stuff that happened in the 20th century. Other theories? Yeah, so my theory, which because deep learning is not all that interpretable, which I know I complained about at the beginning of my talk, so I'm not trying to do everything all at once. I'm trying to do little things all at once. But my theory about why Martin Van Buren appears here, so we have a lot of data, and we learn from both Wikipedia and old trivia questions. And during the 1990s, there were lots of questions about Martin Van Buren actually written from the show Seinfeld. And so there was an episode of Seinfeld where the protagonists were threatened by the Van Buren boys, which had, I guess, this is their gang sign, so because Martin Van Buren was the 8th president. And so Martin Van Buren himself was a pretty forgettable president, but there were lots and lots of questions written about Martin Van Buren in the context of Seinfeld. And so that's my theory about why he ended up in the 20th century. Yeah.
Okay, so you have a pretty big machine learning program to create your vector field using machine learning algorithms.
Mm-hmm.
And then you use those, then you take those averages from that vector field that you created.
Yes, exactly.
Is the first step
Yeah.
word2vec?
So we initialize using word2vec and glove. We also did word2vec and glove. We use that to initialize our embeddings, but then we use backprop to update those embeddings. Okay, so that's how you answer a question, but how do you figure out when to buzz in? And so this is work with my student, whom you may remember from the interpretation part of the talk. And so we need information from experts. So just like we had the oracle for the interpretation part, we need to figure out when we should buzz in. And so what we did is we built a little web app so that people could play Quiz Bowl online. So this turned out to be really popular. We had hundreds of people using it in the first 2 weeks that we launched it. We had tens of thousands of questions answered, so it was great. When we got the data we needed, we shut it down. And then afterwards, folks at Berkeley and MIT created bootleg copies of it. It was so popular. And so if you want to play Quiz Bowl, you can go to a site called Protable, created by one of our bootleggers. It's quite a bit better than ours, I must say. So anyway, we have a bunch of data about when humans buzz in on Quiz Bowl questions. And so what we do is something similar to what we did in the interpretation part. So we have questions come in one word at a time, and we generate some guesses. And we get a feature vector out of that, and then we learn that in situations like this, we can't answer the question correctly and beat our opponents, so we'll wait. Then we get some more information, we have more guesses. We think that in situations like this, we can't beat our opponent, so let's wait some more. Then we get more information. We're pretty confident now, and we have a different feature representation. In this case, yes, we can answer it correctly, so let's buzz in. So this is fairly similar to what we did in the interpretation part. We have a lot of examples of what we should do. We use that to train our algorithm to learn when it should answer the question correctly. And so there's some neat stuff that's happening. So here's a question. He left unfinished a novel whose title character forges his father's signature to get out of school and avoids a draft by feigning desire to join. And so there are no named entities in here. There's no sort of high TF-IDF terms in here where you could match this up to an author like Thomas Mann. And what's nice about these approaches is that it's able to figure out how to combine these things together to answer these sorts of questions. So we have all the boring experiments that we need to do in academia. You can see our papers for that. Other things that we're doing is we tried out our algorithm in matches against other people. So here we played a game against 4 people who won a lot of money on Jeopardy. And it was sort of embarrassing. The game ended in a 200-200 tie. We assumed that there would be a blowout in one direction or another. And so after the game was over with a tie, the system just shut down and people had to go home. And so we couldn't resolve that. So that was embarrassing. So the humans declared that they won that because our computer refused to play more. Later we matched up against Ken Jennings, who had won more than all of the previous people combined. And we did manage to win that 300 to 160 in Seattle. And so we're able to do that. But the story isn't over yet. The Quiz Bowl community complained, well, Jeopardy ain't Quiz Bowl. We all know that Quiz Bowl is a much purer trivia competition than Jeopardy. And so more recently, we played against some of the world's best quiz bowlers, and we got stomped. There are videos on my webpage of that. And so we played against the best team from California, and they beat us by about 20 points. We played against the best quiz bowlers of all time, and they beat us by about 150 points. So we still have a long way to go. So here are some places where we're having issues. So anyone know who this is?
Trump?
Yeah, Donald Trump. And so our algorithm knows about Donald Trump. It's seen a lot of questions about Donald Trump when he was the host of The Apprentice. And so our system still thinks that Donald Trump is the host of The Apprentice. Would it be so? So it answers Chris Christie, which not too far off, but still not right. And then it also has a really hard time with popular culture. So our algorithms are out of touch. And so part of the problem is that song titles aren't always very distinctive. And it also has a problem with things that change a lot. And so pop culture, they're sort of flavor of the week, and it has to learn about all this new music constantly, and it just can't keep up anymore. It has to go to bed. And so anyone know who this is? Australian rapper whose album, The New Classic, contained Fancy. Okay, this is Iggy Azalea. And so, but our system thinks that it's Bruce Springsteen. So, so we're working on trying to get it to be a little more hip and able to keep track of newer events. And if you are interested in this, we have now opened it up so that anyone can submit their algorithms to play this game. So we have shared tasks, and so in 2017, we'll have a new competition against another group of top quiz bowlers, and if you think that you can do this task well, please submit your system and do better than we do, and beat those pesky humans once and for all. Okay, but that's not all. One of the reasons that I got into doing this is that these matches are exciting. It's a way to engage people, and so for both the game against Ken Jennings and the Jeopardy chance, we had hundreds of people show up. It's a good way to get high schoolers interested in machine learning and using computers to do interesting stuff. I also found something really interesting. While we were playing against the Jeopardy champions, we were displaying what the computer was thinking off to the side. And I taught machine learning a number of times, and if you know machine learning algorithms, you know that a lot of these algorithms contain dot products of two vectors, and you use that to make a decision. And so that's a hard concept to teach. There's an interesting intuition there that takes a while for people to grasp. These 4 people, who are all liberal arts majors, learned how to read dot products pretty darn quick, and they were very quickly able to understand when the computer was completely off in left field and when the computer was close to making the right answer pop up. And so if you incentivize people correctly, they will learn machine learning. And this was the most effective that I have ever taught dot products in a decade of being a professor. I think this is another reason, beyond just entertainment value, why we should have machines, algorithms, competing with humans. Okay, so another example of competition is some work done by Vlad Nikolai as a student at Cornell. And we looked at the game Diplomacy. Who here has heard of Diplomacy? All right, so this is sometimes called the game that ruins friendships. One of the interesting things about this game is that unlike, say, Risk, which is another board game where you have pieces moving across a map and you're trying to take over the world, there's no randomness. And so everything is decided by conversation. And so the way the game works is that you talk to each other and you move units around. And we'll see an example of this in a second. But the great thing about Diplomacy is that people play it online. And so we were able to get a bunch of games where people played Diplomacy online. And so let's see how this game works. So here, there are 7 players on the board. And so let's say that the Stegosaurus player is trying to work with this guy. And so the Brachiosaurus player. And so the great thing about Diplomacy is that you need to form alliances with your other players. And so if he wants to take Vienna, he knows that he can't do it on his own. So he needs to ask his friend for help. And so he sends a message like this. I need to take Vienna, why don't you help me to get in there? And so he does that, and we get a nice computer-readable sign that these guys are friends. And he succeeds, everybody's happy except for whoever was in Vienna before. And then we have this friendship, but the friendship ends when the Brachiosaurus moves into Warsaw and betrays his former friend. And so in the game, this is called stabbing, short for backstabbing, so when one player betrays the other. And so then we have another nice machine-readable signal that they aren't friends anymore. And then we also have more messages afterwards, not really sure what to say, except that I regret you did what you did, and presumably this friendship is over. And so this is a neat data set, because in every game you're going to have friendships, because you can't win on your own without the help of your surrounding players, and betrayals, because if you want to win, you can't let anyone else survive. And so you're going to have friendships. All of those friendships are going to end in betrayal at some point. And so can we use machine learning to try to understand what's happening in these interactions? So let's take a look at graphs that look something like this. And so we have time before betrayal. So we're going to normalize all the time so that betrayal is at the very right hand here. And so at the beginning, most of these values for various things are going to be near 0. It's balanced between the person who is doing the betraying and the person who is betrayed, the victim. And so we can look at how much they use positive words like great, awesome, thanks, how polite they are, could you, please, would you, yada, yada, and talking about the future in 3 rounds, I will, things like that. And so if you look at positive sentiment, going right up to betrayal, the person who is going to betray you starts getting really nice. And talking very positively about all the great things that will happen if you are friends with me. And so they're really laying it out thick, talking about how great everything is. And you can see the divergence between the betrayer and the victim. So we can also look at politeness. And so this is actually a little bit interesting. So the politeness actually goes down a little bit over time. And you'll notice that what's happening is that the victim is increasing their politeness and the betrayer is decreasing theirs. So it's not just one-sided. So in this case, it was all pretty much one-sided. The betrayer was laying it on thick. But here, sometimes the victim has some inkling of what's happening, and they're trying to stave it off. And this is actually something you see in marriages as well, where you have one partner making increasing demands of the other, and then sort of you're making demands, and then you withdraw, and you're sort of resigned to what's going to happen. And we can also see something similar with future planning. People stop talking about the future. And so people stop talking about the future. They don't want to make plans. They don't want to slip up and get caught in any of their lies. Okay, so that was very quick. That was a fun example of how we can have machines look at the messy interactions that are part of the everyday world. And if we want to have algorithms that truly interact with us, they need to be able to understand not just our search queries, but also the messier parts of the human condition. And so the very last thing that I want to talk about is building on that understanding in not a game, but something with higher stakes that could be in a similar framework, politics. So this is work with my student An, who is now at Facebook. And traditional political scientists use something called ideal point models to understand political candidates. And one problem for ideal point models is the Tea Party movement, which is a recent phenomenon in American politics. Tea Partiers don't fit in sort of the traditional left-right spectrum of American politics. And so can we capture this using machine learning techniques? And another problem of recent politics is that not everyone has a voting record. So traditionally, political scientists understood the politics of individuals by looking at how they voted on bills. And so especially recently, we've had governors, entertainers, and CEOs becoming political candidates. They don't have a voting record. Political scientists can't sort them in the ways that they traditionally have. But all politicians by definition talk a lot. And so can we use that to understand where they fall on the spectrum? And so the ideal would be to say, take Ben Carson's Twitter feed and use that in conjunction with the votes and the commentary that we do have for political actors to map everyone into the same consistent space. And so we're not going to do Twitter. In this case, we're going to look at congressional floor speeches, but we'll develop a machinery that one could apply to Twitter. And so the intuition is that people reveal how they place themselves on the political spectrum by what they say. And even if you just look at Republicans, there are different ways of talking about a particular policy issue that reveals where you stand on this political spectrum. And we want to be able to capture this. So the way that we're going to do this is we have a bunch of people, and we want to place them on some political spectrum. And we want to do it for each individual issue. So the intuition is that there are words that define an issue that are nonpartisan. There are words that simply define what it is to talk about, say, healthcare. But there are ways of framing this issue that reveal where you stand on the spectrum. So if we use sort of the traditional left-right and repurpose it for identifying conventional Republicans from insurgent Republicans, if you talk about affordable care and exchanges and helping the poor, you're more on the traditional side. If you're talking about the unconstitutionality of the Affordable Care Act and how it's a government takeover, you're more on the insurgent side. So we want to be able to discover this automatically. So our first experiment I will skip over because I'm running short of time and want to leave plenty of time for discussion. but we're able to predict whether you're a Tea Party member or not better than methods that just use a vote. And if you don't have votes, you just have the text, we do much better than obvious baselines. And, yep.
So aren't you assuming here that the politicians are saying what they mean?
Yes, absolutely. Yeah.
And isn't that a dubious assumption? And isn't your goal to predict what that particular politician is likely to do in the future? And so wouldn't it be prudent to broaden your predictors? Look at maybe the amount of money given would be a better predictor than what they say.
Yeah, so there are two parts there. So the first part is that we're assuming that people mean what they say, and so it's not quite as bad as that because we still have for the people who vote, we still have how they vote, and so that's sort of putting your money where your mouth is, figuratively. And so if you talk like people who vote in a particular way, even if they talk in weird ways, the votes will line up, and that's okay. And I'll show an example of that in a second. But you're right. If you want to look at, say, allocations and expenditures, that might be a more honest way of doing that. And I'm collaborating with some folks at Boulder, and we're trying to do that. Yep.
What about politicians' votes?
What about them?
Like could you do predictions based on what they say as well as what they vote for?
Yes, exactly. Yes, and that's what we're doing. So here we're predicting not just so these numbers have to come from somewhere, and these are coming from the people who do vote. So not everybody votes, but some people do, and we're seeing where the people who do vote fall on the spectrum. And so we can see places where actions match with the vote. So traditional Republicans and insurgent Republicans from the Tea Party on these issues talk about them in the same way and vote about them in the same way. So there's no daylight on civil rights, minority issues, civil liberties between Tea Party Republicans and traditional Republicans. If we look at, say, macroeconomics and government operations, the government shutdown, they talk and vote completely differently. So it's quite obvious that there's a schism there. You don't need a fancy algorithm to tell you that. But what is interesting is that they talk very differently about these issues, but they vote in the same way. So for example, on healthcare, you have traditional Republicans, mainstream Republicans, talking about healthcare in a very different way than the insurgent Republicans, but they vote the same way. Everybody wants to repeal the Affordable Care Act. So no difference there. What I think is surprising is that there are other issues where they talk about them in the same way, but vote on it differently. And so these are cases where mainstream Republicans are getting things done by crossing the aisle and working with Democrats, or the insurgent Republicans aren't a big enough force yet to really change this. But this is where we might see future schisms that we're not seeing yet. Okay, so I've talked about algorithms that inform, collaborate with, compete with, and understand their human users. And I think this is important because we've been seeing a lot of fear about the future of artificial intelligence and machine learning. And I think a lot of that fear comes from people not understanding what is going on inside this black box. And a lot of people have developed this fear that we're going to be living in a science fiction dystopia where artificial intelligence and machine learning is coming to kill us, coming to get us, coming to take our jobs. And that's not completely irrational because most people don't understand what machine learning and artificial intelligence can do and what it can't do, because it's a black box. And the more that we open this up, the more utility people will get out of machine learning and artificial intelligence, and the less fear there will be around this issue. So I have a very young daughter, and one thing that I've noticed is that play isn't just about a way of passing the time. It's really an important way to socialize young intelligences. And through play my daughter is learning how to interact with the world, what social norms are, how to know what other people are feeling, to experience empathy. And I think we need to have the same regimen for computers. And so we can't just have machine learning and artificial intelligence serving Netflix backends and telling us what to buy. We need to be able to play with them as well, because we need to socialize artificial intelligence and machine learning just like we socialize our preschoolers. Yep.
How do you distinguish your definitions of artificial intelligence and machine learning?
So I use, I'm using them somewhat loosey-goosey here, but I sort of typically think of artificial intelligence as an umbrella over machine learning, and machine learning is one flavor of artificial intelligence.
How would you define artificial intelligence?
Yeah, so I would define artificial intelligence as machines behaving in a way that we would perceive as being intelligent.
It's interesting because I would define it differently. I'm not saying that I'm right.
Right.
You may be right. I define it as a machine having agency or a form of consciousness so that they make decisions on their own.
Yeah, and I think that I would lump a lot of that under intelligence, and so I don't think we're too far apart on that. And I think that if we do have machines that can cooperate with us and play with us, I hope that we can live not in a sci-fi dystopia, but in a sci-fi utopia, where you have intelligences like Lieutenant Commander Data from Star Trek, who helps you solve the problem of the week on the bridge of the USS Enterprise, and then you go back to Riker's quarters afterwards and play a game of poker. And if we need that so that we can have machine learning and artificial intelligence that understands not just what humans are going to do when they're driving an autonomous vehicle on a road, but when a human is afraid, when a human is concerned, when a human is worried. Okay, so that's all I had. I'm happy to talk more. I want to thank my collaborators and my funders and people who give me data. So that's all I have. Happy to talk more. If you're ever in Boulder, please stop by and say hello. Or if you're interested in any of these problems, or you want to arrange an exposition game of Quiz Bowl with our robot, let me know, and we'll try to set something up.